Seems like I am streaming. Is the voice too high? Let me see. The voice might be too high.
On a room.
Right. That was Peaky Blinders.
Uh,
Yep. Seems like I am. Yeah, the voice is fine. Yep, the voice is fine. And now we will begin with this modern assembly language 160. Page number 160. Is that it? Where we were yesterday? We had successfully completed the exercises and then we had to get into abstract data types. We understood this. That is what are pixels and stuff. And I want to see what does dot EQU mean. What I guess is it means that the label here is equivalent to this thing on the right, to this number, or if there is an address or whatever is on the right, that label can be used as a replacement for that. And when the program is compiled, that label will be replaced by the value that it refers to. Now, dot EQU mean in assembly. EQU instruction means equate means set this symbol equal to this value. Yeah, that is essentially like a variable. Okay, and then yep, here we were. Word frequency counts. Counting the frequency of words in written text has several uses. In digital forensics, it can be used to provide evidence as to the author of written communication. Different people have different vocabularies and use words with differing frequency. Word counts can also be used to classify documents by type. Makes sense? Scientific articles from different fields contain words specific to the field, and historical novels will differ from Western novels in word frequency. Okay. Listing 6.4 shows the main function for a simple C program which reads a text file and creates a list of all the words contained in a file. A list of all the words that are contained in that file, okay, along with their frequency of occurrence. Along with their frequency of occurrence, that is amazing. The program has been divided into two parts, the main program and an ADT, abstract data type. The ADT is used to keep track the words and their frequencies and to print a table of frequencies. Abstract data type. Okay, here are things that I include then in this part of the code, which we analyzed yesterday. But again, we are going to go into that. We do remove punctuations, copies the input string to a new string, but omits any punctuation characters. Okay. This function takes it a pointer to a string, to a character that is essentially a string, and wo- sorry, this returns a string and also takes in the string, and the word here refers to the input string. Then it initializes a new word that is a new string, which is equal to the length of the input string plus one, because the length would only contain the characters that are visible and also the new line, but it would not contain the um, it would not contain the null terminating character at the end of the string. So we have to have one more byte for that. Then we take a current destination and current source variables, which will be pointing to the current letter, current character in the input and the output string. Then, while current source is not equal to 0, that is, till we have not reached the end of the string, do this. What do we do? If stir character, stir chr, we pass it in, we pass in two strings to this function equal to null. Okay, what does structure in C? Geeks for geeks, I guess. The structure function in C is a predefined function in the string.h library. It is used to find the first occurrence of a character in a string. It checks whether the given character is present in the given string or not. If the character is found, it returns the pointer to it. Otherwise, it returns a null pointer indicating the character is not found in the string. Structure const takes in a string and a character, but here we are providing it a string and go to the current source, that is the current character. Okay, if this string contains the current character, if this string contains if this current character equals any of these symbols here, then we will get the address for that, which will not be null, and thus this if block will not be executed. But if it is not contained, then it will be equal to null, and we would have the current destination equal to the source character, but its lowercase value, and then we would update the current destination pointer by one so that it points to the next byte, and no matter the result of the if block, we will still update the current source character by one byte so that it points to the next character. And after this has happened, we would have all the characters from the source to the destination except these ones, and after that we put the current destination equal to 0, that is the last character in the current destination will be equal to 0, and then we return new word. What is new word? New word is the first character in the destination. That makes sense. The main function reads space, white space, separated words. White space, the main function reads white spaces, separated words from standard in, removes punctuations, and generates a word frequency list. Okay, we got main here. Into main max word length. This is the maximum length of a word. Then we have next word and clean word, which both are a string, and we have word list type, which is a list, and word list is an abstract data type, I would suppose. Then we have next word. This string is equal to it has how many bytes? Size of a character multiplied by maximum word length. So next word has been allocated a space which can store a word this long, 1024 bytes long, characters long. Then we have a list. This list which we declared here but it did not initialize. It will get whatever is the output of WL alloc. Right line alloc? I don't know. Then while scanf percentage next word equal to 1. That is, we will be scanning the string, whatever is. If it is equal to 1, that is, we are actually scanning. If when the scanf returns the number of inputs that it has scanned. So when we have one output by scanf, that is, we are not, we are at least or like we are exactly taking in one string from the standard input, which is our keyboard, and then we will get into this function, and it will be stored in next word, which is a pointed to a string. Next word here, for which we got memory here. Now, next word equal to remove punctuation next word. Okay, clean word. Okay, we got clean word, which is a new string which has all the punctuation removed from next word. Now, if stir length of clean word is greater than zero, that is at least we have one character in that, then we will do WL increment list with the clean word. So this is the interface to interact with the this list type which we are including here, list type or functions which we are including here. Then we free clean word after adding, because clean word is not added as it is, it is um it is not added as it is. A copy is made and a reference to that copy will be stored in the list. So this part scans the words and adds them to the list. Now print alphabetical list. Now we want to print list, and for that we do WL print and pass in the list which we created here, right here, WL alloc, and then we print it. Yep, and then we print numerical list, and we do print numerical and pass in the list, and then we free the list, and then we return 0. Next, the interface for the ADT is shown in listing 6.5. These There are several ways that the ADT could be implemented. Note that the interface given in the header file does not show the internal fields of the word list type. Thus, any field which includes this header are allowed to be declared pointers to word list. Okay, the interface is here. The interface is defined here, but the internals, the interface given in the file does not show the internal fields of the word list data type. Okay, what the data type contains, it does not show. Yes, that makes sense. Thus, any field which includes this header are allowed to uh, declare pointers. Shit, it has function yet, yes. Thus, any field which includes this header are allowed to declare pointers to word list data type but cannot access or modify any internal fields. That makes sense because we do not know what the internal fields are. We are just importing the word list data type and declaring a pointer to that. And to work with the word list data type, we have to pass it on to the functions which are also declared in this, and those functions already know what the word list data type contains. Okay, the list of words could be stored in an array, a linked list, a binary tree, or some other data type or data structure. Also, the subroutines could be implemented in C or in some other language, including assembly. Yes, listing 6.6 shows an implementation in C using a linked list. Note, the function for printing the word frequency list in numerical order has not been implemented. It will be written in assembly language. Since the program is split into multiple files, it's a good idea to use the make utility to build the executable program. A basic make file is shown in figure 6.7. Okay, so listing 6.7, we have quite a bit of listings. Here is the header file for word list ADT abstract data type. If not defined, then define. Okay, so if list h is not already defined, then define it. What does it do? Define an opaque type named word list. Okay, type deck struct wlist. Its name will be this. We are type defing the structure wlist into word list. Okay, then WL alloc allocates and initializes a new word list. Okay, it initializes a new word list. Okay, it returns a pointer to a word list, WL alloc. Then WL free frees all the storage used by a word list. It takes in a word list and returns void. WL increment adds one to the count of the given word. If the word is not in the list, then it is added with a count of 1. Makes sense? Does not return anything, but takes in a word list and a character, a string, a word, and adds it to the list. Now, WL print prints a table showing the number of occurrences for each word followed by the word. Takes in a word list and prints. Doesn't return anything. Then WL print numerical prints a table showing the number of occurrences for each word followed by the word sorted in reverse order of occurrence highest to low. It takes in a word list but does not return anything. Then we end F. Implementation of the word list ADT. Okay, here is the implementation for the word list ADT, and that is crazy. It spans quite a bit. It still includes dot list header. The list node, the word list node type is a linked list of words and the number of times each word has occurred. Linked list whose each node contains a word and the number of times that the word has occurred. So yes, wlist node, a node contains a word and count and a variable called next which points to a structure called wlist node, which is this. And we are type defing this whole structure into wlist node. Makes sense. Okay, but why do we have to type def it? Can't we just use wlist node word here, right? Let's see. Oh, um, yep, yep. Ah, nope. Tab makes the pointer go to some other place. Oh, I can copy the spaces and print them here. Well, fuck you, Sam Altman. So now here is why do we have to use type def here? Why can't we just write word list node instead of wlist node? This seems like a very stupid question because I do not understand, but it provides convenience and improves readability. Let's break it down. Without type def, if you declare the structure like this, then every time you want to declare a variable to this type, you must use struct wlist node. Okay, we will have to use struct wlist node explicitly. Struct wlist node extract pointer head null. Okay, with type def, instead of using this whole thing, I can just use wlist node, a node, and a pointer to that. Okay, that makes sense. Here I have a pointer to it, but here I am the wlist node itself. How does that work? Yes. Yeah, instead of this, I can write this directly here without type def, but then I would have to use struct wlist node every time that I want to use this data type. That makes sense. And but here, what are they doing here? In this example, you gave me in the for in the second line we are initializing initializing a variable called head, which points to which contains a pointer to a word list node. But what are we doing in the first line with the node variable? What does that contain? Does it has a pointer to the word list? What does it contain? Is it a pointer or what? Let's break it down line by line. Well, there are only two lines, but still. Word list node, the first one. This declares a variable node of type word list, which is the type definition name for a struct. Okay, so if I do node dot next or node dot something, node dot word, I will get the word, the string, and if I do node dot count, I will get the number count. But for me to do that with head, I will have to use a star head and then do that. That means go to the location at the head and then look there for count or look there for word. Okay, that makes sense. This declares a variable node of type word list node, which is a type def of struct word list node. WList node. Node is not a pointer, it is a direct instance of word list structure. It means node is an actual structure, struct object stored in memory containing character pointer, a pointer to a string, character pointer, a pointer to a string, and a pointer to an integer, and a structure word list, a pointer to the next node in the linked list. It means node is an actual struct object stored in memory. Okay, stored in memory. But the thing is that in the we are actually storing a pointer to that. This is just abstraction. We are actually using a pointer to that, right? However, since node is a normal struct variable, not dynamically allocated, its next pointer is uninitialized unless explicitly set. Wordless node head. No, head is a pointer to a wordless node, not an actual node is a pointer to a word list node, but not an actual node. It is initialized to null, meaning it currently does not point to any valid node. This is explicitly used at the as the starting point for a linked list. Okay, I declare this here. Then in the main function, I have a node and I put node.word, node.count, node.next equal to null since it is not a part of the list. Now I declare a head, which is a pointer, and then at I make head equal to the address of node. So in head, I am storing the pointer to the node thing. Yo, Technoblade never dies. Okay, but in actuality, both head and node store a pointer to the um, structure, not the actual structure. The difference is only in the way that data is accessed from them. Data is accessed from them. But at the assembly language level, they both are only labels to used to refer to a memory location which contains a pointer to the structure, right? And both of these pointers are stored in the stack, right? Right? You are thinking deeply about how memory works, which is great. But there is a small distinction to clarify. Concept at sea level. Word, you are thinking deeply. Baffle me. Concept at sea level. Word list node and pointer allocates the actual structure in memory on the stack. Oh, allocates only a pointer which may or may not point to a valid word list node. That makes sense. That makes sense. Memory layout at assembly language. At the assembly language level, everything is just memory addresses. However, the difference lies in what those memory locations contain. Word list node. Word list node. This. Okay, so this has a pointer which actually points to some space in the memory which can contain our structure. But the pointer which we declare in this line has only a single has only a space which can contain a pointer if you initialize it, but and it does not allocate some memory to store that structure. Okay, memory layout at assembly language. At the assembly language level, everything is just memory. However, the difference is lies in what these memory locations contain. Word list node. This allocates memory for the entire structure. Word list node. The structure's field, word count, and next are directly stored in the allocated space. In assembly, node is just a label referring to the start of the structure. If node is on the stack, it might look like this. Word pointer contains 8 bytes, which these 8 bytes contain the address for the first character of the word that we are storing here. And count takes up 4 bytes. Then we have a padding to make it good, 4 byte padding so that everything is nicely aligned at 8 bytes. And then we have a pointer which also contains an address to the next one, word list head. So this is equivalent to this 8 bytes next pointer, word list head. This allocates only a pointer 8 bytes on a 64-bit system on the stack. The pointer does not yet point to a valid structure unless explicitly aligned. In assembly, head is a label referring to memory location that stores an address. Head is referring to a memory location that stores an address. Makes sense. This only allocates a pointer that is 64 bytes. But when using this, I get a pointer which actually points to in the memory to something in the memory to a location which can store data. It actually allocates memory for my structure to be stored at. If head equals the address of node is executed, then head will store the address of node. Stack memory layout. After word list node and word list this is declared, low memory head address node. Okay. Oh, head address. At the head address, I get the address of the node after I do this. Then at the node address contains all of these. Okay, so it does not contain an address to a pointer. It actually contains the thing. It actually has the first address to the thing. It does not contain a pointer to it. It actually is the first address to it. Okay, that makes sense. Head list contains a pointer which points to the structure. If you go at the address of head list, at that address you will see another address which points to the structure. But if you go at the address of the head list, it contains the actual structure, the first byte that stores the actual structure. And this is how it works. Node is not a pointer, it is the actual structure, which means its fields are directly in memory. Head is a pointer to a structure, which means it only stores an address. It only stores an address, yes. Both head and node reside in the stack unless malloc is used, which would allocate on the heap. At the assembly level, both node and head are memory labels, but a node holds actual structure data while head only holds an address. Let me know if you want. Assembly snippet for a deeper look, and for a deeper look, why are you giving me a rocket? But okay, that was good, and I have low battery. Whoa, let me charge. I might also have low battery on my phone, which acts as my camera. My camera guy is my phone. That is just crazy technology we take for granted. Yep, perfectly aligned. Nope, to go a little bit to the right. Yep, now I am perfectly aligned. And my voice is getting to you guys too. That is crazy. Okay, now here. Type def, type structure. We did this. Yep, we were trying to understand why we have to use type def here. Now, word list type holds a pointer to linked list and keeps track of the number of nodes in the list. Okay, it contains a pointer to the head of the list and an integer n words which contains the number of words in the list. Then WL_alloc allocates and initializes a new word list. It returns a pointer to a word list. Oh, which is fucking hell. And here is the function for that. What do? We create a variable called temp, which is a pointer to a word list. Then temp gets some memory, which is the size of word list. And if temp is null, that is, we do not get anything, any result, any memory, then we print unable to allocate word list and exit with a code of 1. But if we do get some memory, then we put number of words equal 0 and the head will point to null. Then we have WL free, freeze all the storage used by a word list. This should be recursive, a loop or something. Yeah, see, word list node temp and temp B, temp A and temporary B. Okay, they both contain to a word list node. Okay, temp A points to the head of the word list. Now, while temp A is not equal to null, that is, we still have something to deallocate. What do? We store the address for that in temp B, and in temp A, we store the address for the next one, and we free the word, only the string at temp B. And okay, first of all, we free the string at temp B, and then we free temp B itself. Because if we first free temp B itself, then the pointer, then only the space which is taken by the pointer, which points to the word, is freed, not the word itself. So first we free the word and then we free the address that is storing the word. And then we move on and do it. till it is null, and at the end we we, we, we free the first we free the storage that is taken by the word list structure, which stores the count and the a pointer to the first list node. Then we have WN lookup is used internally to search if the list of words to search the list of words. It returns a pointer to the word list node. Okay. If the word is not in the list, then it returns a pointer to the place where the word should be inserted if the insertion point is the head of the list. Then it returns no. Okay, if word is not in the list, then it returns a pointer to the place where the word should be inserted. If the insertion point is the head of the list, is the head of the list. If the insertion point is the head of the list, that is the word should be inserted at the head. Now, does that mean when the list is empty and has nothing? That would make sense. Word returns a word list node, a pointer to a word list node. Okay. Word list node returns a pointer to a node. And this is the name of the function. It takes in a pointer to a word list node and a string. Okay, here, uh, yep, we have word list and word list node. Okay, this one takes in a pointer to a node and returns a pointer to a node and also takes in a word, a pointer to a word. Now, what does it do? Word list node previous is null. Previous is null. We have a variable which contains null and can contain a pointer to a node. Now, while first is not equal to null. First lst is not equal to null. What do we do? Is not equal to null, and at the same time, string we compare the strings at the correct current node, and the word is less than 0. That is, they are not equal. Then we make the previous variable point to the first one, and the first one point to the next one. The first pointer uh, will point to the next node in the list, and we will also preserve the pointer that it originally the node that it originally pointed to. Now, at this loop will end when we have a full comparison, a good comparison, or the list has ended. Now, after the while loop has executed, is there something of problem? Nope. Obvious is working fine. Now, if first is not equal to null, that is, we actually found what we were looking for, and still is not equal to null. This means that we have not reached yet the end of the string, and the word at the current point equals the word that has been given to us as an input. Then we return that list, or otherwise we return the previous node. The previous, what is previous? Previous. We return previous. Previous contains the node, which is the last node, whose next is null. And now here we have WL increment adds 1 to the count of the given word. If the word is not in the list, then it is added with a count of 1. That makes sense. Does not return anything. It takes in a pointer to a list and a word. Now, word list node, we have a new word, which is a pointer to a word list node. Declare a pointer to a node, and we have another pointer w list, word of the list, which is the output return value of wn lookup, which to which we give in the head of the list, that is the head of the list, and we give in the word. We will So if we get no, that is this word is does not exist on the list, then what do? We compare the word. Oh, no. Either it is this, or either that the word is not contained in the list, or it can be that we compare the word returned with the word, and they are not equal. So this means I this whole expression means that the word was not present. WL equal to null means that the word was not present, and this means that the word is not present. Like basically mean the same thing, but they have to check for different cases. So they are checking if the word was not given. But if it was that we found the word, then we increase its count and nothing else. But otherwise, we have to add it, add a new node to the list for the new word that we got, and it is not in the list. For that, what do? We go to the list and increase the number of words, first of all. That makes sense. And we get new word here, new word which we declared here, and it has the size of a node. And if we don't get it, then we print that which memory has been taken, and we don't have anything. Otherwise, we make the word equal to struct word, that is stir string duplicate. We get a pointer to a new string which is stored in that, which is and that pointer is stored in the word field of the new node, and make the counter equal to 1. That is there is only one instance for this word because this is a brand new goddamn word. And then we check if the pointer is null. We check it if the pointer that is given to us by this function lookup is null. That is, we have to store it at the head. We have to store the new word at the head of our list, at the start of our list. Therefore, the new words next will point to the head of the list, and the list's head will be updated to point to the new word. Else, that is, we have a place where we can insert this. So what do? We insert it. What do we do? What do we do? We insert it. We have the new words next will point to the next word at the place, and the next word the will point to the next node from the node where we have to insert our new node, and after that the next node will be updated to point to the new word within this. Its next points to the next, and then the mm, so new words next will contain the pointer to the next, right? And then the pointer which earlier originally used to point to the next will be pointing to the new word, and the new word will be pointing to the original next that the list contained. Or here we have this. Then we have a function which prints wlist, takes in a list, and wlprint prints a table showing the number of occurrences of each word followed by the word. Number of occurrences of each word followed by the word. Void wlprint does not return anything, only takes a list and pointed to a list called list. Then it initializes pointed to a node called w list, and that will point to the head of the list. Okay, then while w list is not no, that is we still have a node to be printed. What do? We print 10 decimal places till 10 decimal places. We print an integer and then a string. And what is the integer? The integer is the count for the current that is stored in the current node, and the word is the word in the current node. And then we make wlist point to the next one, and then after that there are d unique words in this document, which is equal to the integer into n words property of the list type. Then we have wlist number prints a table showing the number of occurrences of each word followed by the word sorted in reverse order of occurrence, that is high to low. Makefile for the word frequency program. God damn it. What is this? Okay. We have C obj equal to this. This one was a C implementation. And this is a make file. What the heck is a make file? We have terminal commands incoming here. Okay, I guess this is the file that we execute to make our project, to make a single compilation file for our project, because the code is distributed in different files. So this links them and makes a single combined file. Hmm. Okay, if we have a .depend file, include it. Suppose this is listing 6.7. If a basic make file is shown in listing 6.7. I don't know what the heck is a make file. We will get to it after reading a bit. Now, suppose we wish to implement one of the functions from listing 6.6 in Arch assembly language. We would delete the function from the C file, create a new file with the assembly version of the program, and modify the makefile so that the new file is included in the program. Makes sense. The header file and the main program file would not require any changes. The header file provides function prototypes that the C compiler uses to determine how parameters should be passed to the functions. As long as our assembly function confirms to its C header file, the program will work correctly because at the end of the day, the C and the assembly language will be first converted to object files, which will be linked by the linker. So does not matter if it is C or assembly. It is only a user side thing. Sort by word frequency. The linked list is created in alphabetical order, but the WL print numerical function is required to sort it in a reverse order of number of occurrences. There are several ways in which this could be accomplished with varying levels of efficiency. Possible approaches include, but are not limited to, these are the possible approaches by for reordering the list. Reordering the linked list using an insertion sort. Insertion sort is an sorting algorithm which can be used to insert to sort a given list. How does it work? It goes through the list the number of times that there are elements in the list. If there are n elements in the list, then this program goes through the list n number of times, and each time it goes through the list, it starts does not start from the first element. It starts from the first element of the list which has not been sorted. So every time it goes through a list, it uh, sorts one element. So the first time it starts from the first element of the list, and at the when it reaches the end, it finds the smallest element and inserts that at the first element and puts the first element where it found that smallest element. And then the next loop starts not from the first element because it has been sorted already. It is the smallest element or the largest, depending on how you are sorting. It starts from the second element and goes through the list, finds the smallest, replaces that element with the element that it started with, and then it starts with the third element and goes on. Insertion sort. Reordering the linked list using insertion sort. This approach creates a completely new list by removing each item one at a time from the original list and inserting it into a new list. Oh, you can insert it into a new list if you want. New list sorted by the number of occurrences rather than the words themselves. The time complexity, software update schedule light. I will not show my password to you. Into a new sorted by new list sorted by the number of occurrences rather than the words themselves. The time complexity for this approach would be O power n big of n square, which would require no additional storage. However, if the list were later needed in alphabetical order or any more words were to be added, then it would need to be resorted in the original order. Sorting the linked list using a merge sort algorithm, which is a recursive algorithm, and it sorts like a bitch. It sorts very fast, divides the list to be sorted in like by two every time, and merges those smaller sorted lists. Merge sort is one of the most efficient sorting algorithms known and can be efficiently applied to data in files and linked lists. The merge sort works as follows. The sublist size I is set to 1. Okay, that is the smallest list that we have to sort. Then the list is divided into sublists, each containing I elements. Each sublist is assumed to be sorted because there is only one element. How you cannot sort that, it is already sorted. Assumed to be sorted. A sublist of length 1 is sorted by definition. Yes. The sublists are merged together to create a List of sublists of size 2i where each sublist is sorted. The sublist size I is set to 2i. The process is repeated from step 2 until I is greater than equal to n, where n is the number of elements to be sorted. That makes sense, doesn't it? It is merge sort. The time complexity for merge sort algorithm. Shit, that is too dark. Like, and the time complexity for the merge sort algorithm is big O of n log n, which is far more efficient than the insertion sort, which is n square. This approach would also require no additional storage. However, if the would also require no additional storage. However, if the list were later needed in alphabetical order or any more words were to be added, then it would need to be reordered in the original alphabetical order. We create an index and sort the index rather than rebuilding the list. Each since the number of elements in the list is known, we can allocate an array of pointers. Since the number of elements in the list is known, we can allocate an array of pointers. Each pointer in the array is then initialized to point to one element in the linked list. The array forms an index, and the pointers in the array can be resorted in any desired order using any common sorting algorithm such as bubble sort, in place sort, in place insertion sort, quick sort, and into login or others. This approach requires additional storage but has the advantage that it does not modify the original linked list. That makes sense. We can sort the array instead of sorting the whole goddamn list. There are many other possibilities for reordering the list, regardless of which method is chosen. The main program and the interface header file need not be changed. Different implementations of the sorting function can be substituted without affecting any other code. Because the implementation of the ADT is hidden from the code that uses it, this separation of interface and implementation provides many benefits. That makes sense. The WL print numerical function can be implemented in assembly as shown in the listing 6.8. God damn it, you are writing that in assembly. Okay, that is cool. The function operates by reordering the linked list using an insertion sort. By reordering the linked list using an insertion sort described above, listing 6.9 shows the change that must be made to the makefile. Now, when make is run, it compiles the two C files and the assembly file into object files, then links them all together. The C implementation of WL link print numerical in list.c must be deleted or commented out, or the linker will emit an error indicating that it found two versions of WL print numerical. Now they have written an assembly code for that thing. Shit. This is the makefile, the new makefile, which is used, not can be, which is used to convert the two C programs and the assembly code into object files and then link them later. And this is the assembly code. Okay, that is goddamn scary. But break it into smaller parts and we got this. And during this stream, no frames have been dropped. That is crazy. Maybe I can Increase the bit rate. Okay, increasing the bit rates, and let me see how the stream. That is crazy. Maybe I can. The stream has, I would say, yeah, good quality. That is good. That is good. Okay, I was sleeping there. That is good quality. Acceptable. Acceptable. One watching that is me. Even the quality in stream is good. Stream is good. Es ist gut. Es funktioniert. And now AArch64 assembly implementation of this function will print a list with sorted numbers where the number of words, the count of each word is sorted from the highest to the lowest. And we have some definitions in the start. The link, these are the offsets. Okay, the offset for the word is 0, the offset for the count is 8, the offset for the next pointer is 16, and size is total 24 because after 16 the next pointer takes 8, so 16 plus 8, that is 24. Definition for the word list type. Word list, the word is at the zero offset from the start. Head has an offset of 8, and that's it. The size is 16. We have equal to null. Null means 0. That is very counterintuitive. The sort numerical function sorts the sort numerical function sorts the list of words in reverse by number of occurrences and returns a pointer to the head of the reordered list. Records with identical counts will maintain their original ordering with respect to each other. Records with identical counts will maintain their original ordering with respect to each other. The zeroth register holds head of source list head. Okay. The first register holds the destination list head. The second holds pointer to node currently being moved. Okay. Source, destination, node currently being moved holds pointer to the current node in the destination. Okay. Current in the destination and the current node that is should be pointed. And the fourth register holds pointer to previous node in destination list. To the previous node in the destination list. That makes sense. And the fifth register holds count of current node in destination list. Count of current node in destination list. That is where should it be put in the destination list. And then W sixth register holds count of node currently being moved. Count. That is the number, how many times that word is there. Okay, then we have a tie. Declare that sort numerical is a function. What does it do? Where is the global thing? Here, WL printed numerical global. What happens in the sort numerical function? It stores first the frame pointer and the link register onto the stack and move the value of null into the first register. And Okay, so the first register contains destination. Destination is 0 at this point somehow, and the 0th register contains the head of the source, contains the head of source list head. And then we have loop A, and we also have loop B. It compares if the source has run out of elements. Okay, and what does it do? It branches if they are equal to end loopa here, here, and which just moves the destination to the 0th register, the destination list to the 0th register, and loads back the things that we stored and returns. But during the loop, if they are not equal, then we dispatch first node from source list. Dispatch. Okay, we move to the second register, the first node, and we load the value of the first count and the next. So we update the next register with the value of the next node, and we get the count into the fifth register for the current word. Then we find location to insert into the destination list. For that, we move in the contents of the first register, which is null 0, into 3. Destination comes into current, and then we move null into fourth. That is, previous is null. And then in loop B, we compare. What do we compare? We see if the third register is equal to null. Well, it is equal to null. So we have to found why is it equal to null? Because we have the value of the first register into the third register, and here we initialized first with null. So here we have contents of the third register equal to null. Okay, and okay, the contents of the previous register have been updated by null, and the current register, the third register, is supposed to have holds the pointer to the current node in the destination list. Holds the pointer to the current node in the destination list. Fourth holds the pointer to the previous node in the destination list. So the current node in the destination list is null. Null, and x1 holds destination list, which is null, and x2 holds pointer to the current node being removed in the current list. Okay, okay. We load the count and the next from there, and we compare the contents of the third register with null, and if they are equal, if it is null, that is the destination node is null, then we go here. What do we do here? We store the contents of the third, which is null, at the next, and compare fourth with null, which is null, and conditionally select and save the value of the second register, that is the source, current source, into the first register, and if they're not equal, then we keep the value of the first register in itself, and then if they are equal, that is the fourth and null are equal, then we loop back to A. Okay, I do not fully understand this, but let me see what this does. Stores the pointers, and it stores the 0th register contents, stores The content of the zeroth register WL print numerical prints a table showing the number of occurrences for each word followed by the word sorted in reverse order of occurrence. I think I will be able to write this on my own. It will take some time, but I will write this and understand this better. But here we are, stores the pointer, the value at the save pointer to the word list at the stack. Yes, we got 16 bits of more memory on the stack. You load the value at the head. That is the first string. That is the first node in the list. And then we branch link to sort numerical, which sorts the numerical it numerically. And then we load into the first register the head back into the first register, and then we store the contents of the zeroth register at the head, that is the new first node at the head of the link. And then we move 0 into 1. And what does 1? 1 contains the address for the list, and then we print the list. Then we store back our get back our frame pointer and link register, and we just return. This is the make file. We are moving on. We will be we'll be doing the exercises at the end, which would that is about big ass program. This is a single program. That is oh, from page number 168 till page number 176. It spans across 250 lines. It is cool. It is to improve the performance. And then we have another long program. Then we have ethics, case study, Ethicrack, history of Ethirac. That would be interesting to read. An overview of design flaws, and then we have some stuff. We have chapter summary, and then the questions. Questions are going to be really good. That will be really good and fun. Referring to previous question, given the following definitions of for a stack ADT, write the init stack function in R. So yeah, we are skimming through the programs given in the chapter, but at the end, when we actually do the exercises, we will be going deep and understanding, because reading does not, theory can only take you so far, right? As someone said once to me directly. The word frequency counter, as previously implemented, takes several minutes to count the frequency of words in this textbook on a Raspberry Pi. Several minutes to count the frequency of words in this book on a Raspberry Pi. Most of the time is spent building the list of words and resorting the list in order of word frequency. Most of the time for both of these operations is spent in searching for the word in the list before incrementing its count or inserting it in the list. There are much more efficient ways to build ordered list of data. So we are going into efficiency. That is cool. Since the code is well modularized using an ADT, the implementation mechanism of the list can be modified without affecting the main program. A major improvement can be made by changing the data structure from a linked list to a binary tree. Makes sense. Essentially, cutting the search time by half, not half, but log of n would be the new search time. Figure 6.1 shows an example of a binary tree. Count left, right, left, right, left, right. but actually implementing a binary tree and inserting the values at the correct place. That is going to be tough. That is going to be tough. Yes. Sorting word frequency. Well, all these algorithms and data structure things, I have planned to do them. I will do them next year. Yes, next year. Right now, I have other things planned. So, sorting word frequency counts. The time required to insert into a list is on. First, we have to find the element and then list. But the time required to insert into a binary tree is log 2 often. To give some perspective, the author's manuscript for this textbook contains about 125,000 words. Since log 2 and divided by this is less than 17, we would expect the linked list implementation to require about, and this is the original one, and this times as long as a binary tree implementation to process the author's manuscript for this textbook. In reality, there is some overhead to the binary tree implementation. Even with extra overhead, we should see a significant speed up. Listing 6.10 shows the C implementation using a balanced binary tree instead of balanced. Yes, that is the thing, balanced binary tree instead of a linked list. And this is the goddamn balanced binary tree we define. There is a thing function called max which returns if x is less than y, it returns y, the greater one. Otherwise, it returns x. Oh, abstract data types. This chapter deals with the fact that you can write code that performs some function, and then you can create a header file which specifies the interface through which the code can be used by the user using the code, and they do not have to worry about the low level details of how the code is running and how the things that they are trying to do are happening. They just have to care about the interface. Abstraction. So this function implements a balanced binary tree. Well, I believe you. It is a long as function, long as code. Okay, here we define max, and here we have a little word definition. Oh, most of it is shit. It is not same to the last one. The structure of a node, word list node, has changed. First, we have a word, then we have a count, and then we have two variables, left and right, which is store a pointer to a node, and then we have height, which indicates at which height we are in the binary tree. Okay, then walloc allocates and initializes a word list node. It takes in a word and it returns a pointer to a node. What does it do? It makes a new word variable which points to a word. It gets space by malloc, and then if new word is null, that is we did not get any space in the memory, we print an error message. Otherwise, we make the word, we duplicate the word provided to us in the input and save the pointer to the new word in the new nodes word section, and the count is 1, and we put left and right equal to null and height is 1, and we return new word. WLN freeze the storage of word list. Okay, what does it do? If root is null, then it just returns. Otherwise, it frees the word at the root and then freeze the left and freeze the right and then freeze the root. And here WLN lookup is used for searching the binary tree. It returns a pointer to the word list. If the word is not in the list, then it returns null. Returns a pointer to a word to a node, and this is the name of the function. It takes in a pointer to a node and which is called root and a word, the word that we want to look for. What does it do? It initializes an int called compare. If root is not equal to null, that is we have something to look forward to. What does it do? We see the comparison value. We compare the word with the current word, the inputted word with the word in the current node. And if compare is less than zero, which means that it is lexically lower, the word that has been provided to us is lexically lower than the word at the current node, then we look for it in the left part of our current node. Otherwise, if it is lexically greater, then we look for it in the right part of our current node, and then whatever is the result, we return it. Boolean height finds the height of a node and returns 0 if the pointer is null. Because if null is 0, if node is 0, then the just takes in a pointer to a node, and if the pointer is null, it returns 0, that is the height is 0, otherwise it returns the height that is okay. You had to make a function for that, but okay. WLN balance finds the balance factor for a node and returns 0 if the pointer is null. Balance factor. That is just crazy. We need to know quite a few things to understand assembly. We need to know binary, we need to know have a background in C. What if I didn't knew anything about the C programming language and this was my first time learning any code? Well, I would not start with binary, but I would not start with assembly, probably with JavaScript or Python or Rust maybe, or C++ or Zig or Haskell, something. Now, WLN balance takes in a pointer to a node, and if the node is 0, then okay, and then returns the balance. Oh, height of the left minus height of the right. So if one of them gets, if left has a lot of elements, more number of elements than right, then we have a problem. Or if right has a lot of elements, then also we have a problem. So, and we would get something that is not 0, and something that is not 0 is not good. Okay, and WL in rotate left rotates counter. Okay, that is rotation. It is in algorithms, and here we are trying to understand assembly, not algorithms. So I think we can skip over this code. Yep, and this code is not even in C language, it is in assembly. We can skip over this code. The main essence is that this code implements binary trees to save the linked list which we were storing in a linear function. This stores them in a binary tree function like this. And we know the theory, but here is just its implementation. And it is good. Now moving on here. We can have an indexing and sorting by frequency. Yo, we can have an array which points to other numbers, which we can have an array which array of pointers. Shit, my battery of the phone is going down. Nope. I will have to see if the phone is charging still. Nope, it is not. Yes, it is. It is not charging. Yup. I hope it keeps charging. Hope. Or what can I also do is I can change the screen and oh shit. Oh yeah, I can do this, and I can use my phone from my laptop. That is just crazy, literally crazy. I would have to unlock my phone, which I cannot do currently because it is acting as a camera. But okay, just I will just move on with this stream. Yep, refresh, and yes, we can have an array of pointers where each pointer points to a node, and instead of updating the left and right columns of each node, we can update the order of those pointers in the index, which would be much more simple. Indexing and sorting by frequency. With the tree implementation, WL print numerical, okay, could build a new tree sorted on the word frequency count. Word frequency counts, however, it may be more efficient to build a separate index and sort the index by word frequency counts. That makes sense. The assembly code will allocate an array of pointers and set each pointer to one of the nodes in the tree. Okay, as shown in figure 612, this figure. Then it will use a quick sort to rearrange the pointers into descending order by word frequency as shown in figure 6.3. This implementation is shown in listing 6.11. This is the implementation. The the this much, only this much, and here is how it is. Binary tree of word frequency with sorted order. Here the first one sorts to the highest, points to the highest, then this one points to the second one, third one points here, here, which is the third in descending order, then the fourth pointer points here, the fourth one in the descending order, then that, and then to one, the first. That makes sense. And this assembly code, what does it do? This assembly code makes a new array and makes this array whose each element is a pointer, and it points to other to the nodes, right? And then after doing that, it runs a quick sort algorithm and sorts these pointers in the order so that the first pointer points to the node whose count is the largest, and the last pointer points to the node whose count is the lowest. That is in decreasing order, and this is the implementation for that. and we are going to skip over it, and because why? Why? Because reading this big ass code would not help us as much as getting to the exercises and then doing the exercises, because this is just an implementation for an algorithm. This is a DSA part. So we can go to the next thing. The tree-based implementation gets most of its speed improvement through using 2n log n algorithms to replace, yep, n square algorithms. Yes, that makes sense. These examples show how a small part of a program can be implemented in assembly language and how to access C data structures from assembly language. The functions could just as easily have been written in C rather than in assembly without greatly affecting performance. Later chapters will show examples where the assembly implementation does have a significant better performance than the C implementation. That makes sense. And then ethics case study. Thirac 25. The Thirac 25 was a device designed for radiation treatment of cancer. Okay, we will complete this whole section and get to the summary of the chapter here today only. But before that, I will have to take a small break and go to the washroom as a person does. No alarms and no surprises. No alarms and no surprises, please. Now, Ethics case study. The Thrak 25 was a device designed for radiation treatment of cancer. It was produced by Atomic Energy of Canada Limited. Okay, a device used for radiation treatment of cancer, which has previously produced the Thrak 6 and wait a minute. Yeah, which had previously produced the Thrak 6, and from Thrak 6 they went to Thrak 25. Makes perfect sense. And Thrak 20 units in partnership with GCGR of France. It was capable of treating tumors close to the skin surface using electron beam therapy, but could also be configured to megavolt X-ray therapy to treat deeper tumors. The X-ray therapy required the use of a tungsten radiation shield to limit the area of the body that was exposed to the potentially lethal radiation produced by the device. That makes sense. The Therac 25 was used a the Therac 25 used a double pass accelerator which provided more power in a smaller space at less cost compared to its predecessors. The second major innovation was that the computer control was a central part of the design rather than an add-on component as in its predecessor. Most of the hardware safety interlocks that were integral to the design of the Therac 6 and 20 were seen as unnecessary because to software would because to soft because to software would perform those functions. Okay. Computer control was intended to allow operators to set up the machine more quickly, allowing them to spend more time communicating with patients and to treat more patients per day. It was also seen as a way to reduce production costs by relying on software rather than hardware safety interlocks. That makes sense. There were design issues with both there were design issues with both the software and the hardware. Although this machine was built with the goal of saving lives between 1985 and 1986, three deaths and other injuries were attributed to the hardware and software design of this machine. Death due to radiation exposure is actually slow and painful, and the problem was not identified until the damage had been done. History of Thrax 612. This is amazing. AECL Canada Limited was required to obtain US Food and Drugs Administration (FDA). Something FDA approved US Food and Drug Administration approval before releasing the Thrac 25 to the US market. They obtained approval quickly by declaring pre-market evidence because they had evidence that their device is working in the market already, so they have pre-market evidence effectively claiming that the new machine was not significantly different from its predecessors. This practice was common in 1948, in 1984, but was overly optimistic considering that most of the safety features had been changed from the hardware to software implementations. With FDA approved Food and Drugs Administration, yes, approved CL made the Therac 25 commercially available and performed a fault tree analysis to evaluate the safety of the device. I lost. With FDA approval, AECL made the Therac 25 commercially available and performed a fault test analysis to evaluate the safety of the device. The fault test analysis, as its name implies, requires building a tree that to describe every possible fault and assign possibilities to those faults. After building the tree, the possibilities of hazards such as overdose can be calculated. Unfortunately, the engineers assumed that the software, much of what was reused from the previous Therac models, would operate correctly. This turned out not to be the case because the hardware interlocks present in the previous model had hidden some of the software faults. The analytics analysis did consider some possible computer faults, such as an error being caused by cosmic rays, but assigned extremely low probabilities to those faults. As a result, the assignment was very inaccurate. When the first report of an overdose was reported in AECL to AECL in 1985, they sent an engineer to the site to investigate. They also filed a report with the FDA and Canadian Radiation Protection Board (CRPB). AECL also notified all users of the fact that there had been a report and commented that operators should visually confirm hardware settings before each treatment. The AECL engineers were unable to reproduce the fault but suspected that it was due to the design and placement of a microswitch. They redesigned the microswitch and modified all of the machines that had been deployed. They also retraced their recommendation that operators should visually confirm hardware settings before each treatment. Later that year, a second incident occurred. In this case, there is no evidence that AECL took any action. In January 1986, AECL received another incident report. An employee at AECL responded by denying that the Track 25 fault was at fault and stated that no other similar incident had been reported. Another incident occurred in March of that year. AECL sent an engineer to investigate. The engineer was unable to determine the cause and suggested that it was due to an electrical problem which may have caused an electrical shock. An independent engineering firm was called to examine the machine and reported that it was very unlikely that the machine could have delivered an electric shock to the patient. In April 1986, another incident was reported. In this case, the AECL engineers working with the medical physicists at the hospital were able to reproduce the sequence of events that led to the overdose of radiation. As required by law, AECL filed a report with the FDA. The FDA responded by declaring the Thrack 25 defect. AECL was ordered to modify all the sites where the Thrack 25 was in use, investigate the problem, and file a corrective action plan. AECL notified all sites and recommended removing certain keys from the keyboard on the machine. The FDA responded by requiring them to send another notification with more information about the defect and the consequent hazards. Later in 1986, AECL filed a revised correction action plan. Another overdose occurred in January 1987 and was attributed to a different software fault. In February, the FDA and CRPB both ordered that all Therac 25 units be shut down pending effect and permanent modifications. AECL spent 6 months developing a new correction action plan, which included a major overhaul of the software, the addition of mechanical safety interlocks, and other safety related modifications. So the Thrac was a thing developed by AECL, a company, and was sent to US. And the main difference it had was that from its predecessors was that most of its things, the safety features dependent depend dependent depended fucking hell depended on the software instead of the hardware, and the software seems like it was not that good, and so some people got radiation overdose. Overview of design flaws. Depended The Threat 25 was controlled by a DEC PDP-11 computer. The PDP-11 was the most popular mini computer ever produced. Around 600,000 were produced between 70s and 90. and used for a variety of purposes, including embedded systems, education, and general data processing. It was a 16-bit computer and was far less powerful than a Raspberry Pi. The TRAC-25 computer was programmed in assembly language by one programmer, and the source code was not documented. Documentation for the hardware components was written in French. After the faults were discovered, commission concluded the documentation for the hardware was written in French. That is amazing. After the fault were After the faults were discovered, a commission concluded that the primary problem with the Thirac 25 were attributed to poor software design practices by, by that one programmer design practices and not due to any one of several specific and coding errors. This is probably the best known case where a poor overall software design and insufficient testing led to loss of life. The worst problems in the design and engineering of machine were the code was not subjected to independent review. It had no documentation. Right? Oh, it was not subjected to independent review. That makes sense. The software design was not considered during the assessment of how the machine could fail or malfunction. The operator could ignore malfunctions and cause the machine to proceed with treatment. Okay. The hardware and software were designed separately and not tested as a complete system until the system was assembled at the hospitals where it was to be used. The design of the earlier Thrax 6 and 20 machines included hardware interlocks which would ensure that the X-ray mode could not be activated unless the tungsten radiation shield was in place. The hardware interlock was replaced with a software interlock in Thrax 25. Errors were displayed as numeric codes and there was no indication of the severity of the error condition. Shit. The operator interface considered the operator interface consisted of a keyboard and text mode monitor, which was common in the early 1980s. The interface had a data entry area in the middle of the screen and a command line at the bottom. The operator was required to enter parameters in the data entry area, then move the cursor to the command line to initiate the treatment. When the operator moved the cursor to the command line, internal variables were updated and a flag variable was set to indicate that the data entry was complete. That flag was cleared when a command was entered on the command line. If the operator moved the cursor back to the data entry without entering a command, if the operator, okay, okay, had an interface with a data entry in the middle of the screen and a command line at the bottom, the operator was required to enter parameters in the data entry area, then move the cursor to the command line to initiate treatment. It makes sense. When the operator moved the cursor to the command line, internal values were updated according to the data in the parameters, and a flag was set in to indicate the data entry was complete. The flag was cleared when a command was entered on the command line. Okay. If the operator moved the cursor back to the data entry area without entering the command line, then the flag was not cleared, and any subsequent changes to the data entry area did not affect the internal variables. Ah, okay, the flag was cleared when a command was entered, but if a person went from the command line back to the data entry fields, the flag did not clear and thus the inputs would not updated according to what the person wrote next. That makes sense. A glow that is horrible. Ah, shit. Wait a minute. I should have charged my phone in the morning. It is charging, but it is not charging. Shit. You Technoblade never dies. No, it is not charging. Okay, I will use my laptop's camera for now. Um, I do that right. Yep, I can hide this just like that and go to my phone for charging. Uh, right. Yep, it is charging now and let me use image. No, 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 no. Image capture device. Video capture device, which is going to be e FaceTime. That is crazy. Okay, that is seems to be upside down. It doesn't transform. Flip vertically. Ah, that is too big, I guess. That is fine. The quality is not good, but it works, right? The phone is also charging. Yeah. So now, yep. Yeah. A global variable was used to indicate that the. Oh, it is underlined. Okay. A global variable was used to indicate that the magnets were currently being adjusted. This variable was modified by two functions and did not always contain the correct value. Adjusting the magnets required about 8 seconds and the flag was corrected only for only a small period of the beginning of this period. Okay, due to the errors in the design and implementation of the software, the following sequence of events could result in the machine causing injury or even death of the patient. The operator mistakenly specify high power mode during the data entry. The operator moved the cursor to the command line area. The operator noticed the mistake and moved the cursor back to the data entry area without entering a command. The operator corrected the mistake and moved the cursor back to the command line. The operator entered the command line area, left it, made the correction, and returned within the 8-second window required for adjusting the magnets. If the above sequence occurred in less than 8 seconds, then the operator screen could indicate that the machine was in low power mode, although it was actually in high power mode during a final check before initializing the beam. The software would find that the magnets were set for high power mode, but the operator setting was for low power mode. It displayed a numeric error code and prevented the machine from starting. The operator could clear the error code by resetting the computer, which only requires one key to be pressed on the keyboard. This caused the tungsten shield to withdraw, but left the X-ray machine in left the machine in X-ray mode. That is crazy. When the operator entered the command to start the beam, the machine could be in high power mode without having the tungsten shield in place. X-ray rays were applied to the unprotected patient. Ah, it took some time for this crucial flaw. It took some time for this crucial flaw to appear. The failure only occurred when the operator initially made a one keystroke mistake in entering the prescription data, moved to the command area, and then corrected the mistake within 8 seconds. Initially, operators were slow to enter data and spent a lot of time making sure that the prescription was correct before initializing treatment. As they became more familiar with the machine, they were able to enter data and correct mistakes more quickly. Even eventually, operators became familiar enough with the machine that they could enter data, making a correction and return to the command line within the crucial 8-second window. Also, the operators became familiar with the machine reporting numerical code errors without any indication of the severity of the code. The operators were given a table of codes and their meanings. The code reported was no dose and indicated treatment pause. There is no reason why the operators should consider that to be a serious problem. They had become accustomed to frequent malfunctions that did not have any consequences to the patient. Although the code was written in assembly language, that fact was not cited as an important factor. The fundamental problems were poor software design and overconfidence. The reuse of code in an application for which it was not initially designed also may have contributed to the system flaws. A proper design using established software design principles, including structured programming and abstract data types, would almost certainly have avoided these fatalities. Peace. Now, chapter summary, and then from tomorrow on, we will start the exercises. That is crazy. And we are already at chapter number 6, about the end of chapter number 6. The abstract data type is a structured programming concept which contributes to software readability, reliability, eases maintenance, and allows for major revisions to be performed in as a safe way. Many high-level languages enforce or at least facilitate the use of abstract data types. Assembly language does not. However, the ethical assembly language programmer will give the extra effort to write code that conforms to the standards of structured programming using abstract data types to help ensure safety, reliability, and maintainability. ADTs also facilitate the implementation of software modules in more than one language. The interface specifies the components of the ADT but not the implementation. The implementation can be in any language as long as assembly programmers and compiler authors generate code that conforms to a well-known standard. Their code can be linked to code written in other languages. That makes sense. Like Rust, right? Poor coding practices and poor design can lead to dire consequences, including loss of life, like we just saw with Rack 25. It is the responsibility of the programmer, regardless of the language used, to make ethical decisions in the design and implementation of software. Above all, the programmer must be aware of the possible consequences of the decisions they make. So what this leads to is, if you do not write good code, you will kill people. You will get people killed. So write good code. If you write bad code, people will die. So write good code. That's it. We're at chapter number 6 right now. And what we did: introduction, GNU assembly syntax, load, store, branch instructions, data processing, and other instructions, structured programming, abstract data types. Here we are. And then we have integer mathematics. That would be cool. Subtraction by addition, binary multiplication, all of binary stuff. That would be cool to understand. Non-integral mathematics, fractions and shit. It is a 60 pages long chapter. That would be cool. And then we have floating point. That is just maths. This would be more related to programming. That is advanced single instruction, multiple data instructions. We can get multiple data with a single instruction. Seemed 80 pages long chapter. That is crazy. Then we have devices, how we can access devices that are connected to our device peripherals. And running without an operating system, that would be crazy for Raspberry Pi or something. There are 12 chapters. We are at chapter number 6. That is cool. And that is the end of the stream, I guess. Not I guess, I know. I am the one in control here. Vector performance, and what else we have? The questions. What are the advantages of design software using abstract? Maybe we can do some of the questions. What are the advantages of designing software using abstract data types? Well, if we are designing software using abstract data types, then when writing a big complex piece of software, and if we are using abstract data types in that, then after implementing the abstract data type, we do not have to think about the implementation. We only have to care about the interface and the results that it gives. And that is it. We do not have to care about how it is implemented. And we can use abstract data types written by other people. So that is some burden taken off our shoulders. Why is the pixel data type hidden from the client code? Well, for privacy reasons, because the pixel data type is hidden because the people who wrote the code for the pixel data type, maybe he does not want others to see how he implements stuff, right? So that's why it is hidden from the client, because the person who wrote it does not want it to be seen by other people. High level languages provide mechanisms for information hiding, but assembly does not. Why should the assembly programmer not simply bypass all information hiding and access the internal data structures directly? Well, they can, but uh, ah, I'm getting a call. Wait, my phone is charging. That is cool. Now, high level languages provide mechanisms for information hiding, but assembly language does not. Information hiding, that is, we can use an abstract data type but not know how it works. Why should the assembly programmer not simply bypass all information hiding and access the internal data structures directly? But what they can, but what will they achieve by that? Their work is only increased if they do that. Yep, their work is only increased if they do that. They can see the internal information in our data structure, but that just complicates things, and for them it is just better to stick to the interface that has been provided by that data type. The assembly code in WL print numerical accesses the internal structure of the word data type node type. Why is it allowed to do so? It is assembly. Should it be allowed to do so? Yeah, it can. Yes, it can. Should. Well, if this is more about rights, if the person writing who wrote word list node data type, if he wants others to see his code, then it is okay. He should be allowed to do it. But if it does not, then others, maybe he can hide it somewhere and do come up with something that lets him hide it. And another factor which determines things is that the purpose of ADT is to abstract away implementation details so that the person using the ADT, the client, can only focus on the interface, not the implementation. Right. So that is why that is another reason to hide the code so that they do not see the complexity. They only care about the interface. Okay, we have 11 questions in this and we have complete 4 questions. We have 7 questions remaining. That is for tomorrow. Yep. Bye.